I want you to imagine that you are holding a perfectly polished mirror. You raise your right hand, and the figure in the glass raises its left, and you lean forward. It leans towards you. Every movement appears reversed, but the underlying behavior remains perfectly matched. Now imagine performing the same experiment with the fundamental laws of nature. Replace right with left, replace particles with antiparticles, replace matter with antimatter. For a long time, physicists hoped that nature would behave like the mirror. Different appearance, same rules, but it does not. And deep beneath the border of France and Switzerland, inside one of the most sophisticated machines human beings have ever constructed, physicists have now watched that mirror crack in a place where it had never been definitively seen before. The LHCb experiment at CERN observed a measurable difference between the decay of a particle made from three quarks and the corresponding decay of its antimatter partner, a baryon and an antibaryon, matter and antimatter, following almost identical physical rules. Almost that last word is the reason you exist. I need to be very precise. CERN did not discover why the universe contains matter instead of antimatter. It did not prove a new force, and it did not overthrow the standard model. But for the first time, physicists observed a phenomenon called CP violation in the decay of a baryon with discovery level statistical significance. The result reached 5.2 standard deviations above the threshold particle physicists conventionally require to call an effect an observation. And that matters because baryons are the family of particles that includes protons and neutrons, the matter of atomic nuclei, the matter from which stars, planets, oceans, bones, blood, and nearly everything you can touch are constructed. For decades, we knew nature violated this mirror-like symmetry in other particles. Now the crack has appeared in baryons. And behind that crack sits one of the largest unanswered questions in physics. Why is there anything here at all? Because if matter and antimatter had behaved with perfect symmetry after the Big Bang, they should have largely destroyed one another. Matter meeting antimatter can annihilate into radiation. A universe born with equal amounts of both should have faced a brutal accounting problem. And yet, when you look around the room you are sitting in right now, the answer is obvious. Matter survived, you survived, and the galaxy survived, and something tipped the balance, and that is the door. And tonight, I want you to understand why a difference of only a few percent in the decay behavior of an exotic particle could become a new path toward explaining the existence of the visible universe. Before we step through that door together, take a moment to subscribe to Deep Field Lecture. If you want to understand where the standard model succeeds, where it cracks, and what may be hiding beyond it, you are in the exact right place. Now I want you to imagine a coin. One side is marked M, matter. The other is marked A, antimatter. You flip it 1,000,000 times. If nature is perfectly symmetric, you expect the long-term outcome to be balanced. Not necessarily every short sequence, but overall, no preference. Now imagine the coin produces one side slightly more often, not dramatically, not enough that you would notice from 10 flips, but enough that after tens of thousands of measurements, the pattern refuses to disappear and the coin is rigged. Hold on to that image because this is essentially what physicists mean when they talk about certain forms of CP violation. The C stands for charge conjugation. Conceptually, it exchanges a particle with its antiparticle. The P stands for parity. It reverses spatial coordinates, rather like looking at nature in a mirror. For a time, physicists hoped that even if nature violated one of these symmetries separately, the combination might remain exact. Transform particles into antiparticles, flip the spatial configuration, perhaps the laws would become indistinguishable. And they do not. CP symmetry is violated. Nature makes a distinction. That fact has been known since the 20th century. In the 1960s, CP violation was discovered in neutral kaons, particles belonging to a category called mesons. Mesons contain a quark and an antiquark. Later, Experiments observe CP violation in other meson systems, including particles containing beauty quarks. The standard model eventually incorporated the effect through the complex structure of the quark mixing matrix. So CP violation itself is not new. The new part is where CERN has now seen it conclusively. Baryons, three-quark particles, the same broad structural family as the proton and neutron. CERN's LHCb collaboration studied a particle called the beauty lambda baryon, usually written as lambda-b. It contains three quarks, an up quark, a down quark, and a beauty quark, also called a bottom quark. Its antimatter counterpart contains the corresponding antiquarks. These particles do not live long. They decay almost immediately after being produced. That sounds inconvenient. It is actually useful. Their decay products become evidence, tracks, energies, angles, probabilities, patterns recorded in layers of detectors surrounding the collision region. Physicists cannot hold the beauty lambda baryon in their hands, but they can reconstruct what it did before disappearing. I want you to imagine walking into a room after a glass is shattered. You never saw the glass fall, but fragments cover the floor. From their positions, shapes, and motion, you can reconstruct the event. Particle physics works like that constantly. The collision happens, unstable particles appear, they decay. The detector records the fragments, and then software and physicists rebuild the invisible history. LHCb collected enormous numbers of proton collisions at the Large Hadron Collider, and inside those collisions, beauty baryons and their antimatter partners were produced, and the researchers searched for a particular decay, the lambda-b baryon decaying into a proton, a kaon, and two oppositely charged pions. Then they studied the equivalent decay of the antimatter particle. If CP symmetry were perfectly respected in this process, the statistical patterns should match appropriately. They did not. The difference was about 2.45%, with an uncertainty of roughly 0.47%. The significance reached 5.2 sigma. The mirror cracked. Now stop for a moment. 2.45%. It sounds small, almost trivial. If someone told you two measurements differed by a few percent, you might shrug. Particle physics teaches you not to shrug too quickly. Fundamental discoveries often live in tiny discrepancies. And the question is not whether the number looks dramatic. The question is whether the laws predict the number should be zero. Imagine a perfectly balanced scale. You place identical masses on both sides, and one side repeatedly drops, not by much, but every time. After thousands of trials, the possibility of random error becomes extraordinarily small. Now the tiny imbalance becomes profound because the issue is no longer the size of the movement. The issue is why the scale has a preference. The coin is rigged, and now we have seen the rigging in baryons. And this is where the story connects to the beginning of the universe. I want you to imagine rewinding everything. Galaxies collapse backward into diffuse gas, stars dissolve, planets vanish, atoms separate, nuclei break apart. The universe becomes hotter, denser, more energetic. Eventually, we arrive at conditions where matter and antimatter were produced abundantly. According to our best understanding, the early universe should have created matter and antimatter in nearly equal quantities. That immediately creates an existential problem. A proton encounters an antiproton. They annihilate. An electron encounters a positron. They annihilate. Matter disappears into radiation. If the symmetry had been exact, the later universe could have been almost entirely photons with only tiny, residual traces of matter. No stars, no planets, no chemistry complex enough to produce biology. No observer asking this question, but that is not our universe. The observable cosmos is overwhelmingly dominated by matter. Where did the antimatter go? This is called the baryon asymmetry problem. It is not a small detail at the edge of cosmology. It is the reason the physical structures around you can exist. Decades ago, physicist Andrei Sakharov identified conditions that a theory would need to generate a matter-dominated universe from an initially more symmetric state. One requirement involves processes that distinguish matter from antimatter. CP violation becomes essential. That sounds encouraging. We have CP violation, problem solved, except it is not. And here is the hard truth. The amount of CP violation contained in the standard model is nowhere near sufficient to explain the observed cosmic dominance of matter. CERN itself emphasizes that the known effect is many orders of magnitude too small to account for the universe's matter-antimatter imbalance. That is the deeper crack. The standard model contains the type of ingredient we need, but apparently not enough of it. Imagine baking bread. The recipe requires yeast. You discover yeast in the kitchen. Excellent. And then you calculate the amount required. You have 1 grain and you need a spoonful. Technically, the correct ingredient is present. Practically, the recipe still fails. That is where particle physics stands. Known CP violation proves that nature distinguishes matter from antimatter, but the asymmetry we know how to generate inside the standard model cannot obviously produce the matter-filled universe we observe. Something is missing. Perhaps additional sources of CP violation exist. Perhaps undiscovered particles participate. Perhaps the early universe underwent processes we have not yet identified. Perhaps neutrinos hold part of the answer. Perhaps the Higgs sector contains more structure. Perhaps entirely new fields were active when the universe was young. We do not know. But every new system in which CP violation can be measured gives physicists another place to search. And that is why the baryon result matters. Not because it solves the mystery, because it opens a new laboratory. Until now, definitive CP violation measurements were concentrated in mesons. Now baryons join the story. The family of particles closest in structural form to ordinary nuclear matter has become another testing ground for the asymmetry. A new door is opened in the standard model, and scientists can begin asking whether the pattern behind that door matches what the theory predicts. And there is a complication. Calculating baryon decays is difficult. Quarks are governed by the strong nuclear interaction described by quantum chromodynamics. At low energies, quarks are confined inside composite particles. You never simply pull one quark out of a proton and place it on a scale. Their interactions are deeply nonlinear. This makes precise theoretical calculations extremely challenging. CERN notes that standard model predictions for the specific baryon CP violation effect are not yet precise enough for a full theory versus experiment confrontation. That sentence is crucial. We have discovered the asymmetry. We have not yet discovered whether its size contains new physics. The coin is rigged, but we do not yet know whether the amount of rigging is exactly what the standard model allows. This brings us to one of the most misunderstood ideas in modern particle physics. New physics does not necessarily arrive as a new particle suddenly appearing as a giant spike on a graph. Sometimes it appears indirectly. A known particle decays slightly too often. An angle differs slightly from expectation. A lifetime is a little too long. A symmetry breaks by the wrong amount. The standard model is so successful that the frontier increasingly lies in precision. We know the clock works. We are listening for one gear that ticks imperfectly. LHCb was built precisely for this kind of work. Its name comes from Large Hadron Collider, beauty. The experiment specializes in particles containing beauty quarks and in studying subtle differences between matter and antimatter. Beauty particles are useful because their decays provide a rich environment for testing the standard model. They are heavy. They can decay through many pathways. Quantum amplitudes interfere. Rare processes can become sensitive to contributions from particles too massive to produce directly. This is a remarkable feature of quantum physics. Something you cannot create can still influence a process. Imagine a bridge vibrating and you cannot see the wind, but the pattern of vibration tells you that something unseen is pushing. Virtual quantum effects can operate similarly. A heavy undiscovered particle might modify decay probability even if the collider does not have enough energy to manufacture that particle directly in an obvious way. This is why physicists measure familiar processes to absurd precision. The unknown can leave fingerprints on the known. CERN's LHCb experiment has another ongoing example of this strategy. A rare decay involving a beauty meson continues to show tension with standard model theoretical predictions in an observable known as P5 prime. CERN reported in September 2025 that the latest analysis still showed the same pattern, but stressed that improved theoretical calculations and more data are necessary before anyone can determine whether new physics is responsible. This is how the frontier actually looks. Not one dramatic red alarm, flashing new physics, several small doors, a baryon asymmetry here, a rare decay tension there, a precision Higgs measurement, a neutrino puzzle. Dark matter is still missing. The standard model survives, but the walls are covered in questions. I want you to look around the room you are sitting in right now, and everything solid around you depends on baryons. The protons and neutrons and atoms are baryons. Your desk, your hands, the planet beneath you, the sun, much of the luminous matter in galaxies. Baryons are not exotic strangers to your existence. They are its architecture, and yet the particular baryon CERN study contains a beauty quark and survives for only a tiny fraction of a second. Why should such an ephemeral particle tell us anything about ourselves? Because the laws governing it belong to the same quantum framework that governs ordinary matter. By studying unstable cousins of the proton, physicists can expose features of the rules that stable protons hide. The exotic becomes a microscope for the familiar. This is one of particle physics' deepest strategies. Nature does not give us direct access to the early universe. We cannot travel back 13.8 billion years and place a detector beside the Big Bang. So we recreate fragments of its physics, high energies, rare particles, antimatter, extreme conditions. The LHC is not literally recreating the Big Bang, but its collisions produce particle species and energy densities that allow us to test rules relevant to a much younger cosmos. And then the question becomes, if the rules treat matter and antimatter differently here, how did that asymmetry operate there? The answer remains unknown, but now baryons are participating directly in the experiment. Think about the sheer weight of this. The universe is filled with matter. That fact seems so ordinary that you almost never question it. A chair is matter, a star is matter. You are matter, but from the perspective of fundamental physics, the abundance of matter is an unsolved anomaly. Why did one side survive? Why did antimatter not cancel it? Somewhere in the laws, initial conditions, or early universe dynamics, nature made a choice, not a conscious choice, a physical preference, perhaps an extraordinarily small one. Imagine 1 billion pairs of matter and antimatter particles annihilating. If only a tiny excess of matter existed beforehand, that residue could survive after the pairs vanished. The universe you see today may be built from a leftover imbalance. Galaxies could be the residue of a microscopic preference. Everything you have ever loved, touched, or remembered may exist because the cosmic coin was not perfectly fair. That is existential vertigo. The matter-antimatter problem takes the largest structures in the universe and connects them to tiny asymmetries in quantum decay. A galaxy contains hundreds of billions of stars, yet its existence may ultimately depend on probabilities differing by unimaginably small amounts in the early universe. We tend to associate importance with scale. Nature does not. A tiny broken symmetry can determine whether a cosmos contains observers. Now I want you to imagine the mirror again. At first it looked perfect, and then Meson experiments revealed the first crack. Later measurements mapped other cracks. Now CERN has found one in baryons. The next question is whether all of these fractures belong to the same known pattern or whether one of them eventually reveals a deeper flaw in the glass. The standard model predicts a CP violation. That is important. This result is not automatically physics beyond the standard model, but the standard model cannot explain the total cosmic matter asymmetry with the CP violation currently known. So the search continues. Additional CP violating effects could appear in quark systems. Neutrinos may violate CP symmetry in their own sector. New Higgs interactions could contribute. Particles we have never discovered may have decayed asymmetrically in the early universe. There are theoretical frameworks involving leptogenesis in which an asymmetry generated in neutrinos or related heavy particles is later converted into a baryon asymmetry. There are electroweak baryogenesis scenarios. There are models with new scalar fields. There are possibilities involving physics at energies far beyond the LHC. None is experimentally established as the answer. This is where human intuition entirely breaks down. We want the universe to give us one culprit, one particle, one event, one equation. Reality may be more complicated. Perhaps the cosmic asymmetry emerged from several ingredients operating together. CP violation, non-equilibrium dynamics, baryon number changing interactions, an expanding and cooling universe. The mystery may not be one missing object. It may be a missing process. Hold on to that image, not a hidden particle, a hidden chapter. The standard model could remain locally accurate while being embedded inside a larger theory that becomes important under early universe conditions. This possibility is common in physics. Newtonian mechanics is not useless because relativity exists. It is an extraordinarily accurate approximation in the regime where we normally use it. Classical electromagnetism is not wrong because quantum electrodynamics exists. It is a lower level description. Perhaps the standard model occupies a similar position. Magnificent, precise, incomplete. CERN's new baryon result does not destroy the standard model. It gives us another way to test where its boundary might lie. This is why headlines saying CERN changed everything need translation. The result changes the experimental landscape. It does not yet change the fundamental equations. And those are different claims. The first is real, and the second remains possible. And scientific possibility becomes exciting when experiments can attack it. The LHC has now entered long shutdown 3 after completing its 2026 collision program, while CERN prepares the accelerator for its high luminosity LHC era. The upgrade is designed to produce far larger datasets in future operation, giving experiments such as LHCb, ATLAS, and CMS more opportunities to investigate rare processes. More data matters because asymmetries live in statistics. Imagine again the bias coin. If you flip it 10 times, you learn almost nothing. 10,000 times, a pattern may emerge. 10 million times, subtle effects become measurable. Particle accelerators are probability machines. Every collision is another trial. The more collisions experiments record, the deeper they can search into rare behavior. LHCb required more than 80,000 relevant baryon decays for this first observation. Future datasets can reveal more decay channels, more baryons, more asymmetries, more precise comparisons, and perhaps somewhere among them, an effect the standard model cannot accommodate. That would be the moment everything truly changes, not when a result is surprising, when multiple measurements point toward a new mathematical structure and survive every conventional explanation. Science is patient because reality is expensive. Extraordinary claims are built slowly. 1 sigma, 3 sigma, 5 sigma, independent checks, new channels, new experiments, a theory catching up, then perhaps a new picture. The Higgs discovery followed that logic. So did earlier discoveries in particle physics. The next revolution, if it comes, will probably not announce itself with thunder. It may begin as a percentage, a decay rate, a slightly wrong angle, a tiny difference between a particle and its mirror. Now I want you to return to the polished mirror we began with. Imagine that it represents the young universe, matter on one side, antimatter on the other. Perfect symmetry would be beautiful. It would also leave almost none of the material world, you know? Instead, the mirror is imperfect. Nature contains asymmetries. That imperfection may be why complexity exists. There is something profound about that, and we often associate symmetry with beauty. Physics does too. Symmetries generate conservation laws, and they organize particles. They reveal deep structure, but a perfectly symmetric universe might have been sterile. Sometimes it is the breaking that creates possibility. A tiny imbalance can produce a universe. A crack can let existence through. Newton taught us that the same laws govern Earth and the heavens. Einstein taught us that space and time belong to one geometry. Quantum theory taught us that nature is probabilistic at fundamental scales. The Standard Model organized matter into a remarkably precise quantum framework, and now experiments are asking why that framework produced a universe almost entirely made from one side of the matter-antimatter mirror. We do not yet have the answer, but the search has gained a new language. Baryons. For the first time, CERN's LHCb experiment has definitively observed CP violation in their decays. The family of particles that builds ordinary matter has joined the symmetry breaking story. And that is why this result matters. Not because it answers why you exist, because it gives physics one more place to look for the answer. Journeys like this, deep into the bleeding edge of human knowledge, require time, deep focus, and a relentless distinction between what an experiment has established and what we hope it may eventually reveal. Below this video, you will see a button labeled Super Thanks. If you choose to support the channel there, you help make these long-form explorations possible. But before we end, return with me to the images we carried through this journey. The mirror taught us to imagine matter and antimatter symmetry. The coin taught us that tiny statistical preferences can reveal fundamental asymmetry. The shattered glass taught us how detectors reconstruct particles that vanish almost instantly. The balance scale showed us why a small deviation can become profound. The bread recipe reminded us that known CP violation is the right kind of ingredient, but apparently nowhere near enough to explain the universe. And the hidden chapter reminded us that the missing answer may be a process from the early cosmos rather than one simple new particle. CERN has not solved the matter-antimatter mystery. It has done something more precise. For the first time, physicists have observed CP violation in a baryon decay at discovery level significance. Matter and antimatter baryons do not behave as perfect mirror images. The Standard Model expects an asymmetry of this general kind, but the asymmetry contained in the Standard Model remains dramatically insufficient to explain why the observable universe is dominated by matter. So the door remains open. Behind it may be additional CP violation, new particles, new interactions, new early universe dynamics, or an explanation we have not yet learned how to imagine. And if one day we finally understand why matter survived, we will not merely have explained an exotic result from a particle collider. We will have explained why there were atoms left over to form stars, why planets could appear, why chemistry could begin, why biology had material to work with, why the universe did not annihilate itself into light, and ultimately, why there was enough matter left for you to be here asking the question,